Hi everybody. Today's lecture in circular motion is on something very, very important and very specific called a centripetal force. Now let's look at a couple of examples here. The first example here is imagine you tied a rock to the end of a string and you're spinning it around over your head. So this is sort of us looking down on the rock as it's spinning around. Now, from what we learned before, anything that's spinning has something called an angular velocity, the speed at which it is rotating. But if it has an angular velocity, it also has at any given instant a linear or tangential velocity. Okay? If you remember, we could link those two together. Linear velocity is radius times angular velocity. Now, if we think about it, there's a rope attached to this rock, which means at any given moment, there must be tension acting on the rock by the rope. And since tension is a pulling force, that tension must be acting down the rope away from the rock. In other words, pointed in that particular direction. Now, the second picture here is imagine a car going around turn. So we're in a helicopter hovering above a car going around what I'm going to call a flat turn. Now, as the car rounds the turn, it's traveling in a circle, so it technically has some sort of angular motion around the curve. It also has, of course, at any given moment going forward, a linear motion. Now, what keeps the car on the road? In other words, if you think about it, if it headed into the road and you suddenly turn the wheel, why doesn't it simply slide off the road? Well, that must mean there's a friction force. And in this case, to keep it from sliding out of the circle, the friction, in this case static friction, has to act inward on the circle. That sort of keeps it moving around that turn without it sliding. Third picture, this is a kind of fun ride. It's sometimes called the Gravitron. It's one of those rides you get into this kind of tight cylinder. It spins around and around faster and faster, and you feel pressed against the wall, and the floor kind of drops out, and you're kind of stuck against the wall. So it's clearly spinning with some sort of angular velocity. Now, at any given moment, you are headed at 90 degrees to that with some sort of linear velocity. Again, we always have this 90-degree relationship that seems to occur between radius and linear velocity. Now, what keeps you in the circle? Now, this is a tough one to think about, but if you think about it, the fact is it's the wall that's holding you in place. Something due to contact between you and the wall. And if we remember, that's a normal force, any force due to surfaces in contact. Well, the normal force actually acts straight towards the middle of the cylinder, against your back from the wall. Now, the last one, this is the idea of the Earth and our moon in orbit around us. Now, of course, the moon, it's in orbit, so it has an angular velocity, and of course it has a linear tangential velocity. So, what keeps the moon from flying away? Gravity. And gravity on the moon has to act straight towards the Earth, the force of gravity. So what do these all have in common? Well, notice that tension pointing towards the center of the circle, that friction pointing towards the center of the turn, that normal force pointing towards the center of the cylinder ride. And the gravitational force on the moon is actually acting at all times towards the center of the Earth. So this must have to do with something that we'll label Fc, or the centripetal force. So the centripetal force is defined as any force that acts towards the center of an object's circular motion. The word centripetal itself actually means center-seeking. And it turns out you cannot have circular motion without a centripetal force. You cannot have one without the other. So that's the other interesting thing. The centripetal force can be any force that we've talked about before that acts to the center. For example, in the first part, since tension points towards the center of the circle, the tension is the centripetal force. In the next one, since static friction acts towards the center of that turn, the static friction is the centripetal force. In the next example, since the normal force acted towards the center of the cylinder, the normal force is the centripetal force. In the last one, since gravity acted towards the center of the moon's motion, the gravitational force is also the centripetal force. So that's the neat thing. Centripetal force can be any force as long as it acts towards the center of the circle. And that's going to be one of the most important things to always do. Identify your centripetal force. Now, because centripetal force is a very special force, it actually has its own equation. Centripetal force is found by the mass times the linear velocity v squared over r, mv squared over r. Okay, mass times velocity squared, all divided by the radius of the circle. Notice that's based on the linear velocity. But we already know that linear velocity can be converted into angular velocity. And so there's a second centripetal force equation in terms of angular velocity, which is mass times radius times angular velocity squared. Okay? They're forces, they're measured in newtons, but they're sort of their own special equations. Let's look at an example, the sling, that rock tied to the end of a string and spun around in a circle. So let's say you have a 0.3 kilogram rock. It's being rotated with a linear velocity at this moment of 20 meters per second on a string that is 40 centimeters long. And we want to know what is the tension on that string. Well, again, the key moment, the key step in what to do here is identifying the centripetal force. And again, since tension acts towards the center of the circle, we can say that tension is the centripetal force. They are the same thing. Now it's just a matter of substituting. Since I have linear velocity, where I see Fc, I want to use my linear velocity formula. I don't want to use the angular velocity one because I don't have angular velocity. So where Fc is, I'll put in mv squared over r. Now I just put in the numbers, right? Mass is 0.3 kilograms, the velocity is 20, only that is squared. Radius of 40 centimeters or 0.4 meters. And I get a tension of 300 newtons. And that's really all there is to that. Simple substituting formula, putting in the numbers, and you're done. That's an easy one. But let's look at a second example. That car rounding the turn. Okay. Now, again, as the car rounds the turn, friction, in this case static friction, because we don't want kinetic, we don't want it sliding, helps sort of keep it in that turn, keeps it from sliding out of the turn. So again, the important idea is that the centripetal force and the friction are the same. Okay? Now, what it says here is the mass of the car is 500 kilograms and the radius of the turn is 100 meters, and there's a static coefficient of 0.6 between the tires and the road. The question is, what's the fastest speed that car can negotiate that turn? Well, again, we're going to sort of play a game of substitution. I want a linear velocity, so for centripetal force, I'm going to use the mv squared over r relationship. But friction, if you remember, static friction had a formula µs, the coefficient, times normal force. So where static friction is, I'll put in that equation. Normal force. Well, it said it's a flat turn. So if a car is on a flat turn, okay, if we were to sort of look at a free body diagram of just the car sitting on a flat turn, well, it would have its weight acting down and the normal force acting up, which means the normal force and the weight part would be in equilibrium because the car is not moving up or down. So wherever I have normal force, I can put in mg. So that gives me this. mv squared over r still on this side. Coefficient times m times g. Now, you have a couple choices here. We know the mass is 500 kilograms, so we could put it in. But it's the same car that's friction's acting on and centripetal force. So if I want to be clever, turns out it doesn't matter whether it's a car, truck, anything like that. It's one of the reasons they set speed limits on turns, because it's for everybody. So now, v squared over r, mu times g. I'm going to multiply through by r, little algebra there. And I'm going to take the square root of both sides. So the v, the velocity, is mu s g r, all under the square root. So it's 0.6, gravity is 10, the radius of the turn is 100, gives me the square root of 600, which means the maximum velocity that this car can negotiate this turn is about 25 meters per second. Yeah, a little more than 50 miles an hour. Okay, so again, that's the way to do it. The key to the whole thing, saying that my centripetal force and my friction force are all the same force. Now think about that car around the turn though. Whenever you maybe have been in a car and someone makes a sharp left, what do you feel happen to your body? Well, most people say, well, it goes to the right. And often people say, well, the reason it goes to the right is because there is some sort of force pushing you to the right. Let's look at another sort of similar example. This says that we have a 5-gram dime and it's placed on the end of a record, if you can remember what a record was, 8 centimeters from the center. Okay, so you've got your record and we're placing a dime somewhere here around 8 centimeters from the center. The record is then spinning at 8 radians per second. And what I want to know is the minimum coefficient of static friction the dime needs to have in order to remain on the record. Okay, now again, for the dime to remain on the record, the friction has to act towards the center of the circle. So therefore, the friction is a centripetal force. So again, now let's substitute. Now be careful because in this case we have radians per second, which is an angular velocity, omega. So we want the centripetal force equation mr omega squared, okay, because we have an angular velocity. Friction is still mu times the normal force. The dime is flat, okay, sitting flat, so that means normal is acting up and weight is acting down. So once again, the normal force and the weight are equal to each other. So I can substitute in. So now I have mr omega squared is mu s mg. Now again, I gave you the mass of the dime, which you could use, or you could just cancel it out, which I always find is easier to do whenever I can. The radius is 8 centimeters, or 0.08 meters. The angular velocity is 8 radians per second, which is all squared. Coefficient we don't know. And gravity is 10. When we multiply this on the one side, we get 5.12. Divide by 10, and we get a minimum coefficient of 0.512. Again, remember, coefficients of friction have no units. So again, that works either way, whether you have linear velocity involved or angular velocity involved. You just have to know which centripetal force equation to use. That might be something called centrifugal force, center fleeing, something that moves away from the center. Well, I got some bad news for you. There is no such thing as a centrifugal force. It does not exist. You see, when that car makes that left, you are not going to the right. You are still going straight. You and the car were going straight. The car went to the left, but your inertia kept you going straight, and you just end up meeting the right side of the car. So there is no mysterious force pushing you outward against the wall, called centripetal force. There is only centripetal forces that exist in circular motion, things that keep you in the circle. So one of the reasons you might slide to the right or slide to that one side is because there wasn't enough friction, enough centripetal force to keep you in that circle. So you cannot maintain any circular motion without the existence of centripetal force. Once the centripetal force leaves, you continue to leave the circle on a straight line, tangent to that point. Hence the reason you think you're going right when you still keep going straight. Now, with the idea of force has to come the idea of acceleration, which means if there is a centripetal force, there must be something called a centripetal acceleration. Well, let's look at that. Again, anytime something is moving in a circle, it has that angular velocity. And at any given moment, it has that linear velocity or tangential velocity. but the direction of force is to the center, centripetal force. Now, if we remember Newton's second law, he said that net force equals ma, sum of forces equals ma. And we learned that whatever direction net force is, the acceleration is in the same direction. Which means that in addition to a centripetal force towards the center, there must be an acceleration towards the center. Now if we look at that, if F equals ma, well, if centripetal force were mv squared over r, well, the m's are the same on both sides. So that gives me a relationship for centripetal acceleration, v squared over r, if I have linear motion. Of course, if I have angular motion, mr omega squared is ma, then the other relationship I get for centripetal force is this. Now I want you to note something very, very important, because this goes against a lot of what we ever said in linear motion. My velocity, whether it's linear or angular, could be constant. And now, where we always said constant velocity means a zero acceleration. Well, that's true. There's no tangential acceleration. But anytime you have circular motion, you have a centripetal acceleration. Always. So even if your velocity is constant, okay, if linear velocity is constant, then angular velocity must also be constant. Now, that means that tangential acceleration is zero, angular acceleration is zero, it's supposed to be an alpha. However, centripetal acceleration is not zero. Anytime there's circular motion, there's a force to the center that's unbalanced. Okay? It's not in equilibrium technically. And if there's an unbalanced force to the center, there must be an acceleration to the center. So very, very, very important concept. A constant circular velocity always has a non-zero acceleration. And that's your centripetal acceleration, something that acts towards the center of the circle. Okay, so that is the idea of centripetal force, any force that acts towards the center of a circle. Note, you cannot have circular motion without the existence of a centripetal force. And along with it, the idea of a centripetal acceleration. That if we have a force acting to the center, we must have an acceleration towards the center. Even though we may have a constant linear velocity or angular velocity, now we're going to have an acceleration. But it only occurs in circular motion. Again, circular motion, kind of a tricky thing. See you next time.